My name is Leonardo Mármol, and I'm going to be talking about a new KeyValue store that we like to call non-volatile memory KV. We claim that it's scalable, lightweight, and is flash-aware in a very unique way. So I'd like to start this presentation by giving a little bit of information about KeyValue stores. And over the last few years, we have seen that they have become the preferred data management solution for internet applications. And one thing that they all have in common is that they provide a very simple interface that, to some extent, is basically get, put, and delete, and some other things in different cases, which allows you to basically store information, fetch it, and delete it when you need it. And something that makes KeyValue stores particular is the fact that when you compare to traditional relational databases, they provide a weaker model of consistency. And this is somewhat important. Now, when we ask the question, what's wrong about all this? The problem is that most, if not all, KeyValue stores, they implement some form of log structure or out-of-place updates. And the main motivation for this was mainly driven by the fact that traditional storage, you get a much better performance if you do sequential writes. And this was also true with older SSDs. However, with newer SSDs, the high-end SSDs, the gap between sequential and random writes is not that big anymore. Because of this, they also require some layer that provides some form of compaction or garbage collection, so you can reclaim all data as you write new versions of the same thing. And of course, this has the impact that creates auxiliary amplification generated by the library itself, by the KeyValue store itself, which has a performance penalty and it reduces the life of NAND flash, which is also critical, especially because the latest generations of flash, they have problems with durability. Now, to give a more precise idea of what we mean by auxiliary amplification, let's look at this very simple stack, which is typical of a KeyValue store. So you have an application, you have a KeyValue store, and an FTL. And for those who don't know, an FTL is basically a software layer whose main job is make the NAND flash look like a block device. And it provides a traditional interface that reads and writes. So what we have here is an application that writes W amount of bytes to the KeyValue store. Says, I want you to store this for me, and it has this size. And the KeyValue store typically has to write to the FTL, besides the data, it has to write some metadata and many other things. Like besides the application, there's some updates of metadata. And also, at some points, you have to do some data compaction, garbage collection. So the main point here is that what the KeyValue store is writing to the FTL is much more than what the application actually stored. So the question is, well, how bad is this situation? Like, is it really that bad? So here we have a graph to give you a better idea of how bad is the situation. In particular, we look at a new KeyValue store from Google. It's called LevelDB, which has a very interesting design in the way information is stored and organized internally. What we have here is basically write amplification, how much data is written by the KeyValue store. So higher values are worse. So in the light gray, we see that the amount of data that we ask to write is 1 gigabyte. And then we see that as we vary the configuration of how the workload is executed, we get that the amount of data that is written to the FTL varies. This is particularly interesting in the case of when you say, I want you to do random writes synchronously. And we see that the amplification varies somewhere between 2.5x all the way to 43x. So depending on the workload that you want to execute, the situation is actually pretty bad. Now, this is another problem that is particularly to LevelDB. In fact, it's a very common problem with all KeyValue stores, because all of them more or less have the same design, in the sense that you have an application and they have some sort of a logging mechanism. So they have to have some data mapping in which you store information to map keys and the KeyValue pairs, and for some data compaction or garbage collection, some way to restore. But when we look at the FTL, and we get a closer look, we see that the FTL does many things that are very similar. Besides providing a standard interface of read-write, it also does logging. Although it is done for a different reason, Here, the reason for logging is basically because you're running an media that forces you to write always out of place. And there's also, of course, data mapping, because you have to have a map between logical and physical addresses. And of course, there is also garbage collection or compaction. So what's clear in this picture is that there is a lot of redundancy. And the question is, well, how do we make this better? So what we're proposing is basically to get rid of this redundancy, the first thing that we need to change is basically the interface. From standard interface, we have to have some extended interface that's smarter than the simple read and write interface. And in particular for our case, if we also change the data mapping to be in sparse data mapping, basically sparse data mapping means that you have, for every physical block, you have many virtual blocks. So you're basically improvising a device, virtualizing it, much like the same way memory is virtualized. So by doing this, we can effectively remove all the things that we don't need because they're basically redundant and replace it by a very simple hashing scheme. And by doing so, we have a KeyValue Store that is linear, and we also get the application closer to the FTL and having all the benefits that are associated to that. Now, what we're proposing is basically a cooperative design that cooperates with the FTL. And one of the nice things of doing it this way is that we minimize the amplification. We claim that we also maximize the performance of the application because the latency of everything is decreased. We also, by using the extended interface, we have things like updates that are done atomically, provided by the FTL itself. And also removing all the internal metadata, we say that we no longer have metadata that is depending on how much data you have stored in your KeyValue store. So the amount of internal metadata is constant and independent of that. So that's a very nice thing to have. And also, we have a performance, we write performance that is very close to the raw device performance. And also, by removing some of the internal metadata, you basically have an implementation has fewer locks, and as a consequence of that, you have higher level of parallelism. So if we look at the classes of KeyValue stores and we classify them basically by disk optimized or SSD optimized, we see that more or less it looks like this. But what we're proposing, what makes us unique compared to other works, is that what we're doing is our KeyValue store is FTL optimized as opposed to be SSD optimized. Now, how do we do this? Let's start by talking about the sparse address mapping. And in this picture, there's a lot of information, so let's break it down a little bit. So the way we read this is there are basically three parts to it. The first one is the actual KeyValue store. Then in the middle, we have the sparse address space, and then the physical memory. So the sparse address is basically, the way we look at it, is we basically divide it into many slots of a fixed size. And then each one of these, in each one of these slots, we write the KeyValue pairs. So by doing so, when you get information when you get like a call for a put, for instance, all you have to do is basically you hash your key, they give you an LBA, and with that LBA you say to the FTL, I want you to write this information in this logical address. The FTL does that, and eventually it knows how to organize your data in the actual physical memory. Now, to do this, we of course make use of the extended interface. And for our implementation, we in particular need the following function calls, and these are exported through the use of ioctls. So we have a call for exist to basically query if a particular LBA has been populated or not. We have atomic rise and atomic strings, which is very nice because all our updates in the KeyValue stores are basically atomic, which is it's a nice property to have because it's easy to think about issues like consistency when your operations are atomic. And of course, we have to have some form of iteration that allows us to fetch all the KeyValue pairs. Now, having something like this, of course, is not relevant only for KeyValue stores. We claim that having such an extended interface is useful for basically all sorts of applications. Now, how do we do hashing and collisions? As I mentioned before, it's if the basic operation consists of a single, you get a put. That key is then hashed. I give you an LBA. and eventually use the atomic write interface to write to your FTL. But of course, every now and then you get a collision. So the way we solve collision is basically by using polynomial proving. So there is, when you get a put, then we check, we initialize a counter and we say, how many times have we tried to do this before? Then you get a hash and you check, is there anything in this LBA? And at this point, you can get a yes or no. If you get a yes, you basically keep trying until you find a new LBA that hasn't been populated. Or eventually, you write to that place. Now, to give you a little bit more information about the hash, the address space is basically a 48-bit address space in which keys are hashed. And then the actual hash itself is divided into two different ranges. We have what's called a key bit range, which basically determines the maximum number of keys that you can store. Basically, how many slots of fixed size you have in your virtual address space. And also the value bit range that determines basically how big are the slots. And of course, you have the invariant that the addition have to be 48 bits. As I mentioned before, we have used polynomial probing, so we try 8 times. And how well does this work? Well, we have here in use cases for a device of 1 terabyte, if we configure the key bit range to be 36 bits, and the bit value range to be 12, with such configuration, we can address as many as 64 billion key value pairs, each of being 2 megabytes in size. And of course, you have a probability of failure that is 1 over 2 to the 40. Now let's see a little bit of numbers to see how this does. So the first of the evaluation that we performed was a maker benchmark that compares our implementation of the KeyValue Stores, that of LevelDB, with the raw device. So basically what we're doing here is we want to see how this scales and compares to the actual raw device. So what we're looking here are throughput numbers, so higher numbers are better. And we see the throughput for both gets and puts. So the black line represents operations that we perform directly on the raw device. Basically, we read and write in the block layer. And we see our KeyValue store, which is the blue line, how in both cases, as we increase the number of threads, we notice that our KeyValue store scales much better than LevelDB as the number of threads increases. In every case, we outperform LevelDB, even when we have fewer threads. And more interesting is the fact that not only we're outperforming it, but we're doing it with operations that are always durable. In the case of LevelDB, when you write, in particular in this configuration, you're not writing specifically to the media, you're writing basically to the cache, and eventually that gets flushed to disk, which is the reason why in the puts, when you have only one thread, you get such a higher throughput, because you're basically writing to memory. Now, another comparison that we did was also for throughput using the YCSB benchmark. And what we have here, it's again throughput, so higher values are better or more desirable. And we see a graph that has multiple clusters of 4 bars. So the orange and red represents our KeyValue stores. The green and sort of blue represents LevelDB with different cache size configurations. And what we see here is that one thing that I should mention is that in YCSB, the benchmark basically consists of 2 phases. The initial phase is the load phase, in which you populate the database, and then the second phase, you run some benchmark on the database. So for both loads and every run phase, we see that number of cell memory outperforms LevelDB, even when you're using 1/4 of the size of the cache. And this is interesting because in the case, even though the configuration of the cache sizes are the same for both systems, in the case of LevelDB, because it's running on top of the file system, it's also benefiting from the file system cache. And also, unlike the case of LevelDB, our operations are always done synchronous and atomically. Now, we also look at the latency of operations. This is the graph of latency for workload A, which is 50% reads, 50% writes. We notice that we look at the variation of latencies over time. And what's really interesting about this graph is that, well, first, you should notice that it's in logarithmic scale, is that over time, well, it's not surprising that we have lower latency because we have higher throughput, but the fact is that when you pay attention to the LevelDB in both synchronous and asynchronous, you see these spikes that seems to happen periodically. And we believe this is a consequence of the compaction, internal compaction mechanism that every now and then spikes the latency. So what's really cool about this, besides the fact that we have lower latency, is the fact that our implementation provides a more stable performance. Our design allows for a more predictable performance, which is always good to have. Going back to the main motivation, which was the amplification, we have here again the same graph, but now including our KeyValue Store implementation, and we see that in every case we decrease the number of auxiliary writes. And again, this is the auxiliary write amplification generated by the KeyValue Store itself, not the write amplification of the FTL internally. So I'd like to conclude with a small summary. That is basically we propose an FTL comparative design that allows for simple KeyValue Store design and implementation, so the size is very small, with a constant amount of metadata close to 0 that is completely independent of how much data you have in your KeyValue Store, provides high performance and high parallelism, and reason for which not much data is not much internal state is maintained inside the KeyValue Store, so you basically have an almost lockless free implementation. And by leveraging the extended interface of the FTL, we have operations to be always durable and atomic. And of course, we have lower write amplification. Our implementation is fairly available in GitHub. And having said that, I'll be happy to take any questions. Thank you for coming.
Hi, Michael Condit, NetApp. So this scheme seems to depend on the flash device exporting a range of LBAs that's 30 times larger than the amount of physical storage you intend to use on it. Now, why would it do that unless you have you tell the manufacturer that's what you want?
Right. This particular design is not, I mean, what I'm trying to say is that it doesn't benefit exclusively our implementation of the KeyValue Store. So if I understand your question is, why would you create a sparse address, right?
I mean, I don't anticipate that flash devices that are, as long as the designers are unaware of what you want to do here, that they would actually give you, what you want is the number of LBAs is 30 times larger than the number of physical blocks you intend to use. But that's not the way flash devices are manufactured. The number of LBAs is maybe 50% more than the amount of physical storage, or twice as much at most.
True. Well, we believe that having such a design has multiple benefits that are not only limited by our implementation. For instance, there is a very nice paper called Flash Tier that proposes a design that is very similar. They also have a theme. There are also theme provision in the design, and by doing so, they can provide a caching implementation that is much more efficient. In addition to that, having a sparse address is also beneficial for some implementation of file systems. In particular, FusionIO has a file system called DirectFS, which makes use of this as well. So I would say that doing so will benefit not only this application, but others, and probably makes sense.
I agree with you. Thank you.
If you are racing to the microphone, I'll ask a quick question. So I have one comment and one question. So there was a paper in last year's FAST, so FAST 2013, which took a similar approach, which is what happens if you sort of co-design the file system and the flash layer, and they used an object-based design, but it had sort of a similar flavor. So if you're not familiar with it, you might look and compare and contrast. The other question, and this actually goes to the previous speaker too, is why the comparison with LevelDB? There are systems out there that perform 2 to n times better than LevelDB on flash devices. So why is LevelDB the thing that people are comparing to?
There was no particular motivation for picking LevelDB. We basically used it for a comparison because it was a new KeyValue Store, and it had an interesting design. And in the web page, they have some comparisons with previous implementation of KeyValue Stores, and they seem to be outperforming some of them. So we say, oh, it's probably a good idea to compare to the new key in town and see how we do. But yeah, definitely, it would be good to see how it compares to other KeyValue Stores.
So what's the cost penalty for declaring a key not found?
Could you repeat the question?
So what's the cost of declaring a key to be not found?
Oh, I see. Well, it depends. When the key is not found, several things could happen. If it's just if you just go and you hash and you find that there's nothing there, then it's very cheap because the exists operation is basically a lookup in memory. However, if you hash and you find something there, you still have to read and then compare to make sure that this is exactly what you're looking for. So in the worst case scenario, you have to do that 8 times. Of course, this is a parameter that you can change, but in the worst case, and it has a very low probability of that happening, as you mentioned, is 2 to the minus 40, which is a very, very small number. So in that remote case, you will have to do IOs 8 times. But in the average case, you get almost 1 IO per operation. Great. Thank you.